All right, anybody else has anything they can still raise? Last time, where we started, here. These are the three theorems, and I motivated them what we are going to do. We are going to consider an action. So as I said, we want to show that there is a subgroup of order p power alpha. That is the existence of Sylow subgroups. And then the two, how many, any two, how do you compare Sylow subgroup, two different Sylow subgroups, and how many of them? These are the second and third theorem. And actually we prove stronger result that for every beta, p power beta, there will be subgroup of order p power beta, where beta is less equal to alpha and alpha is highest exponent of p that divides the order n. And that highest exponent is also denoted by VPN. That is the notation which comes from elementary number theory. All right. So as I said, this is the plan. What is the plan? On the subsets of cardinality p power beta of G. If at all there is a subgroup of p power beta, that must be one of the subset. Right? So, and then G operates on G by Cayley operation, and therefore G will operate on this power set of G, who has each one of them has cardinality p power beta. This is the operation given. This is clearly an operation. You have to note that Gx, if x has cardinality p power beta, and G is any element in G, then Gx also has cardinality p power beta. Therefore, indeed, this belongs to an element here. And therefore, and it's clearly action of the operation condition, that is 1 and 2, are satisfied. And therefore, what I will study is, I will study the orbits and stabilizers of this action. And from there, I want to conclude that it has a subgroup of order p power beta. That is the plan. And not only that, I will actually want to characterize which orbits will contain a subgroup and how many. So this will also help us in counting how many subgroups are there. So everything is going to go together with this group action. And you will see the proof is very, very, very simple. And this proof, another thing, as I said, this was essentially the original proof of Sylow, but Sylow's time there was no group action, so it was not written in group action. So this was the proof which I learned from Wieland's book. And little bit modification that became much, much better proof. And even Hustein's proof will be little different. It is also similar, but there is one lemma which you can avoid here in this proof. That is the advantage. All right, you will see it. And please be attentive. If you have any difficulty, you please stop me. All right, and everybody will understand this proof if you pay attention. If you don't pay attention, nobody can make you understand anything. All right, so our notation, I will write it again here. So G is a group and order is n, and this is p power alpha times q. Alpha is VPN and p doesn't divide q, p is prime. And we have taken any beta less equal to alpha. And we are talking about G operation on the power set p beta G. These are all subsets of x of all subsets x of G with cardinality p power beta. Cardinality of x is p power beta. And the operation is G comma x is going to G times x. This is, you multiply G with all elements of x. So Gx, x is in G, x is in x, and this obviously has cardinality. This is bijective with x, namely the multiplication. So x going to multiplication by G. And obviously the inverse is multiplication by G inverse. That is where group is required. All right, now I want to write down one small lemma which will tell us which orbit will contain a subgroup and how many. That characterization of the orbit. All right, so I will write it as a lemma. So the notation is fixed. So obviously you know the notation. So take any x in p power beta x G. And then I'm looking at the orbit of x. Remember, we are denoting them by G times x. This is the orbit. And that is by definition, we know it is small g times x at G values. All right, now we have only alpha and beta given. And let me put also in this notation, what do I need? I need gamma. Gamma is the difference, alpha minus beta. Okay, then with this notation, I want to prove the following. Then the following are equivalent. This is a short form for the following are equivalent. This I got inherited from my teacher. So 1, 2, and 3. There are 3 statements. And they are equivalent. And the third one is the orbit Gx contains exactly one subgroup. Exactly one subgroup. So this is what we would like to prove. But not every orbit. So it will be conditions. So that 1 and 2 will give you the condition. So the second says cardinality of the orbit should be p power gamma q. Gamma is the difference. So just from the cardinality, you can test whether it contains a subgroup or not. And how many? So exactly 1. And second, the first one, Vp of cardinality of the orbit is less equal to gamma. You see, 1 and 2 are completely combinatorial conditions. And third one is what we want. And you will see the proof is very easy. Proof, of course, will require some knowledge of the group actions, but that all of you know. There will be nothing unknown. So let us write the proof. First, proof of this. All right, so before we write the proof, we write down what do we know from proof actions. We know cardinality of the orbit is equal to index of the stabilizer, isn't it? So we know cardinality of G, which is N, which is equal to cardinality of the orbit or cardinality of the isotropy times cardinality of the orbit. This is orbit stabilizer. This is the isotropy. It is a suffix. And we know what is N. N is P power alpha Q. So let us see, if I assume 1, what happens? So assume 1. Condition 1. So we say that Vp of cardinality of the orbit is less equal to gamma. That is the highest power of P which divide this number is less equal to gamma. And this product, that highest power is alpha. So that implies obviously, if we, these are, remember alpha, gamma is alpha minus beta. So therefore I conclude that Vp of cardinality of the isotropy has to be bigger equal to, can somebody say?
Beta.
Very good. Who answered? Sonakshi.
Yes, sir.
Yes, so it's bigger equal to beta. This is obvious. But that means what? That is P power beta comes as a factor of this cardinality. Isn't it? That means P power beta divides cardinality of the isotropy at X. And maybe more also, but definitely P power beta. All right. Now let us take any X. For any X, X in X, look at the right quotient. G isotropy times X. I claim that this is contained in capital X. Do you agree? See, what does isotropy do? Isotropy fixes is isotropy will tell you G times X equal to X. For any G in the isotropy. Isn't it? So Gx is here. And that belongs to X. That is what I have written. So I have checked this. Therefore, what do we get? From this inclusion, what do we get is the following. Cardinality of this G suffix X times X, this cardinality is smaller equal to cardinality of X, which is equal to P power beta. But this cardinality, this X is also in X. X is in X and X was a subset of G. So this cardinality is no different from cardinality G suffix X. This is also same. Again, the same argument. So since X is in X, which is contained in G. So this is a multiplication map by that small x that gives the bijection. Because X inverse will give you the inverse map. So therefore, what did we prove? Cardinality of the isotropy is smaller or equal to P power beta. But we have just decided P power beta divide this. So altogether, what did we prove? We proved cardinality of Gx isotropy is P power beta. So did we not prove 1 implies, what did we prove? 1 implies 2, we proved it. If I prove cardinality of the isotropy is P power beta, then we know cardinality of the orbit will be equal to P power gamma times Q. And therefore, Vp of cardinality of G X, orbit of X, will be actually equal to gamma, which is alpha minus beta. That's what. So we proved 1 implies 2. If you have difficulty, please ask me now only. This is very, very important and very elegant proof. I will give you 1 minute. Anybody has a doubt that I can explain in some step in between? Sonakshi?
It's clear, sir, to me.
Okay. Tithi?
It's okay, sir.
Very good. So now I am heading to prove. So this is proved already. So I am heading to prove 1 implies 3. So what is given now? Or 2 implies 3, let me prove. 2 implies 3. 2 implies 3. So 1 implies 2 I have proved. I will prove 2 implies 3 and then we will worry about 3 implies 1. And that will finish the proof of the lemma. So 2 is given what? So given 2, that is cardinality of the orbit equal to P power gamma times Q. That is given. And I want to prove what? I want to prove that orbit contains exactly one subgroup. Exactly one subgroup. All right. So look at this is given. So I know the cardinality of the isotropy. That will be n divided by this. So that will be precisely P power beta. And therefore this is a subgroup. So that is Gx is a subgroup of G of order P power beta. But that is not what I want. I want more. My third statement says this orbit should contain the subgroup or not, and how many. All right. So little bit observation and then we will be done. And what does 2? This is by this we know we have used 2 in this. All right. And what is again? If I take isotropy, if I take any x in x and isotropy times this x, we have observed this is contained in x. Again, the same argument. Because if I take any g, that will fix. So again, I will write it here in blue. G times x, small x, belongs to gx, and gx is equal to capital X, and this is true for all g in g, all g in, not all g in g, but all g in the isotropy, and therefore the gx belong there for every g in gx, therefore this whole thing is contained there. This is true for every x in x. But then, once you prove this, what happens? I'm going to multiply this equation by x inverse on both sides. X inverse times isotropy. This is the conjugate of the isotropy by x. This is contained in x inverse times x. And x inverse type x, this is belong to the orbit of x. Because I can take this x inverse as an element in G. Therefore, this is in the orbit. And this is a subgroup. Now, how many, what is the cardinality of this subgroup? Cardinality of this subgroup is equal to cardinality of the isotropy at x, which we have already noted it is p power beta. So I have proved that the orbit, this orbit, contains subgroup. That is a part of statement 3. Contains a subgroup, I got it. All right. All right. Now I have to prove that is the only subgroup it is contained in the orbit. Now anybody has any idea what will I do now? Is this group clear so far?
Yes, sir.
Yes. Rahul.
Yes, sir.
Hello, Rahul. Rahul.
Hello.
Yeah, is it clear?
Yes, sir. It is clear.
Right, very good. So I have to prove that is the only subgroup. But look at this. So let me call this as H. So H is a subgroup in the orbit. Order of H is p power beta. So now can you tell me, this is a p power beta. So H also belongs to this power set of p power beta G. And therefore I can also talk about the orbit of H. But this is an element in the orbit, therefore this orbit should be same as our orbit of X. All right. Okay, but now can you tell me what is the orbit of this H? This side, can you tell me? They are all left cosets, isn't it? So this orbit is precisely the set of all left cosets of H in G. So what are the elements there? So this orbit will look like GH. G varies in G. And H is one of them, because I can take G equal to identity. Any other orbit there? Any other subgroup there? So therefore question has become, when a coset is a subgroup? When can a coset be a subgroup? And the answer, only when it is H. So among these guys, only one subgroup is there, namely H. So therefore conclude that H is the only subgroup in GH, but GH is equal to GX, and that disproves 3. So therefore we have proved 2 implies 3. Again, if you have any difficulty, please raise your concern now only.
So can you please repeat your argument here? That
Which argument?
that GH is equals to GX,
Okay.
and then the only subgroup in GH is H. So
Okay.
H will be.
Sonakshi, can you first of all, do you agree orbit of H is same as orbit of X?
Yes, sir.
This you agree. Fine, very
Yes.
good. This I agree. Now, can you tell me what is the orbit of H? You know, our operation is just multiplication by G.
Yes, sir.
So the orbit of H is precisely the left cosets of H.
Yes, sir.
And among the left cosets of H, who is the subgroup? And how
H.
many?
Only H is the subgroup in GH.
Yes,
The set of all cosets.
that is what I have written.
That is fine to me, but can there? All I want to clarify is that can there not be any other subgroup which is not of the form of GH?
How can it be? How can it be? Tell me. Suppose GH is equal to some K. Then K should have identity.
Yes, sir.
But where is the identity in GH?
H in H.
Yes. Where is the identity? GH. If G is not in H, that is what we are looking, no? Cosets which are not equal to H means this coset we started, it is, suppose it is not equal to H, then it cannot be a subgroup. That is what you want to justify, no?
Yes, sir.
Now, if it is a subgroup, the identity should belong there.
Yes, sir.
But where is the identity there? Because this E, even if it belongs here, it will be G times somebody, G times H. And that H is not allowed to be G inverse because G inverse is not in H.
Yes, sir.
Therefore, E will never be there.
Okay.
So therefore, this cannot be subgroup. This cannot be a subgroup. And that is true for every G not in H. That means every coset other than H cannot be a subgroup.
Okay, sir.
And we are done then. Agreed? Still you have doubt, you can ask me.
No, sir, it's clear.
Okay. Very good. Now I will prove 3 implies 1. So 3 implies 1. So what are we assuming now? We are assuming that orbit of X contains exactly one subgroup. And then I want to compute the cardinality of that orbit and show that VP of that cardinality is less equal to gamma. Right? So start with that orbit. So let Gx be an orbit of X. Remember, X is in P power beta of G, and H belong to the subgroup, the orbit, a unique subgroup of order P power beta in G. And that is contained here, and that is the only subgroup which is contained in that orbit. I am not saying H is the unique subgroup of order P per beta in G. Unique subgroup which is contained in that orbit. And to prove, write down what you want to prove. To prove Vp of cardinality of this orbit is less equal to gamma. So again, if H is an element in that orbit, I know the orbit. So because of this belonging, I say Gx and Gh, they are same. Isn't it? If you have an orbit, if you have any group, any set where G is operating and any orbit there, and if you take a different element in that orbit of that different element is also orbit, the same orbit. Is that clear?
Yes, sir.
So orbit, therefore this orbit is G, orbit of Gx is orbit of H, and orbit of H is the left cosets. And how many left cosets are there? How many left cosets? Then we know cardinality of G equal to cardinality of H times cardinality of G by H. And this I know. What do I know? I know H is of this is P power beta. This is P power alpha times Q. So what should be this? So that implies cardinality of G by H, that is equal to what?
P to the power gamma into Q.
P to the power gamma into Q. But this cardinality is same as cardinality of Gx. Because this is, you want to write one more step, you can write. This is same thing as orbit of H. This is same thing as cardinality Gx. And therefore cardinality I proved this. Therefore, what do we know? Vp of that is actually equal to gamma. But fine, this is also less equal to gamma. So that proves this. 3 implies 1. Remember what is 1. So do you agree that we have proved 1, 2, 3 equivalent? Yes, please.
Yes, sir.
So you agree? Still, anybody has difficulty, I will be happy to explain. This is a very, very nice application of group actions. And now you see we are already finished. We will finish all the three theorems quickly after this observation. All right, so resume the proof. So now let us see what we want to prove now. The statement 1, Sylow theorem. All right, so I have to open up the earlier lecture. So here, what do you want to prove? The number of subgroups of order P power beta is d beta, I am calling it, which is congruent to 1 mod. So in particular, it has to be non-zero. And therefore, there exists a subgroup of order P power beta. And we will know also the number. Right? So that is what we want to do. All right, now, why am I doing this? So let this be here. And let's go to this one. So we are now want to prove that d beta I will improve little bit notation, d beta of G. This is, I am putting this by definition, this is number of subgroups in G of order p power beta. And to prove this number d beta G is congruent to 1 mod p. So if you prove this, what do you infer? In particular, d beta G is non-zero. In fact, it is at least 1. So it is 1, or the next possibility will be 1 plus p. And so on. So, but it is definitely at least 1. So that is G has a subgroup of order p power beta. And also I can take beta equal to alpha. So that we prove the existence of Sylow subgroup. Alright. So I have to prove this. And how am I going to prove this? Now see, as I explained you last time, this set P this set P power beta and G. This is where the G was operating. And we have broken this into several pieces, disjoint pieces, right? And so on. Now this is one orbit, this is another orbit, this is another orbit. And I know when will, and so this orbit, if it contains a subgroup, what is the condition on the cardinality of this orbit? I know. It may not satisfy any one of these conditions. See, if the cardinality doesn't satisfy this condition, then definitely the orbit will not contain a subgroup. So some orbits will contain a subgroup and some may not. So now this will contain, let us mark it. This orbit contains only one subgroup. This contains a subgroup. This doesn't. Or the another one maybe it doesn't. Or another one maybe it is. And I want to count number. Alright, that is the idea. Alright, so what is the cardinality of, so this is the set I have broken into pieces, into the orbits. So what is the cardinality of this set first of all? Cardinality of, I am writing a class equation for this group action. So that is cardinality of this set, that is cardinality of p power p beta G. Can you tell me the cardinality of this? What is the cardinality of this? Can somebody tell me? One, this is a set theory. I want one of you to answer this question. Roshni, can you tell me what is the cardinality?
Yes, sir. It's 2 raised to p raised to beta.
Too complicated.
Sir, it's the power set, no?
Power set of a set G, which has G has a cardinality not p power beta. G has a cardinality p power alpha times q.
So it's 2 raised to p power alpha times.
Huh?
So then it will be set 2 raised to p raised to alpha times q.
That's
That's
not
the cardinality of the power set of
power set of G, whole G. I am asking part of that.
Sir, and use p raised to beta.
Very good. Who is answer? Anuj.
Yes, sir.
This is the cardinal. This cardinality is precisely cardinality of G. Choose P power beta. Among so many elements, I am choosing P power beta, and there are so many possibilities. So this is the cardinal. This is same thing as P power alpha times Q. Choose P power beta. That is the cardinality. This binomial coefficient. Okay, this is the cardinality. On the other hand, I want to use now the class equation. What does the class equation will tell us? Will tell the RHS of class equation I am taking. That is, you take all orbits and count their cardinalities. Isn't it? So count. So this is equal to cardinality sum of the cardinalities of the orbits. That is this, where this sum is varying over the orbit. So this x is orbit. And take all the orbit, not x, gx is orbit. So x is a representative of that orbit. So let me write this. This sum is running over all orbits. Of course, when I say all, that means distinctly. All right, now this sum I am going to split in two parts. The one which contain a subgroup and the one which do not contain a subgroup. So now, this sum is split into two parts. So these are, I am taking the sum of cardinalities of the orbits, and here orbit contains a subgroup. H belongs to a subgroup Hx. Different subgroups will belong to the different orbits. So let me write in words, where Gx contains a subgroup H. And this remaining sum, that is cardinality Gx, where Gx contains no subgroup. No subgroup. All right, now can you tell me what we have proved? If it contains a subgroup, only one subgroup will be there, that we have noticed. And then I can say something about the cardinality of that orbit. See, that is what precisely the lemma says. So what does it say? You look at second. Actually, the second says cardinality of the orbit has to be P power gamma Q. So all these cardinalities in this sum will be precisely summation P power gamma Q. And how many times? If it contains a subgroup. And this subgroup is of order P power beta, obviously. So this sum is going, how many orbits are there which will contain a subgroup? Each one of them will have cardinality so much, and each orbit contains one subgroup. So therefore, this cardinality is d beta g times P power gamma Q. Agreed? Because each orbit will contain one subgroup, and that subgroup will count once. The next orbit will contain another subgroup. They will not be same subgroup because orbits are disjoint. So the number of subgroups of order P power beta, that is how we are denoted. See, the number of subgroups of order p power beta. So they time the cardinality of the orbit, because this sum is taken over so many, this sum is taken over the subgroups. All right, what about this? Then the cardinality is not this. So second says, where is the second? Here. Here it says cardinality is p power this. So it doesn't contain a subgroup. Therefore, what is the negation of 1? The cardinality of the subgroup, VP of that should be bigger or equal to alpha. Bigger than, strictly bigger than alpha. This is equal to, so the negation of this will be, so here this sum is running over the orbits whose cardinality, VP of that cardinality is bigger or equal to gamma. What does that mean? So that means p power not bigger equal to, sorry, b strictly bigger. That means p power, the next power, at least one next power has to divide the cardinality of the orbit. Each orbit in this sum. And I am taking sum of those. So therefore, this plus some number s p power gamma plus. Understood? So we have proved a formula, very nice formula we have proved. So what did we prove? I will write the formula and then you tell me whether do you agree or not. We proved, if you want, this is the class equation. P power alpha q choose p power beta. This is the left side. The right side is d beta g p power gamma q plus some number s times p power gamma plus 1. Wait. S is in some number. So S is in natural number. It may be 0 also. There may not be any orbit. So definitely we proved this formula. Do you agree or not? First tell me this.
Yes,
And
sir.
where you know this number? This is the number of subgroups of cardinality p power beta. Can I pause for 1 minute and ask? So do you agree? Sonakshi?
Yes, sir.
Rahul?
Yes, sir.
I am not able to hear you, Rahul.
Yes, sir. It is clear.
Who else can I ask? Who responds? I will ask to them only. Roshni?
Yes, sir.
So, okay, we have proved. And now, and this we proved it for any group. If I take some other group also, such a formula will be there. This formula, the only number here which depends on the group is this d beta g. Others are just combinatorics. Now, this is the high point. Now, I want to apply such for G equal to cyclic of order n. And why do I want to do that? Because in this case, I know, in this case, we know beforehand what is d beta z mod n. Can you tell me what is d beta z mod n? Roshini.
Yes, sir.
I can't hear you.
Yes, sir. Yes, sir.
What is d beta of z mod n? Sonakshi?
Sir, I'm thinking.
Very good. At least you are thinking. What do you know about cyclic groups? How many subgroups are there?
Sir, is it 1 if beta divides n and 0?
Yes, it is very good because in a cyclic group, for every divisor, there is a unique subgroup of that order. Unique. And this is the number of subgroups of order p power beta. P power beta is a divisor of that n. The same n I have taken. And I want to apply this result for this cyclic group because definitely I know this d beta. And therefore, what will be the above formula for G equal to Z mod n? Right now, close your eyes and write the formula. That is P power alpha Q times choose P power beta. This is equal to D beta Z mod n times P power gamma Q plus some number S. P power, this S will depend also on the group, therefore I will write this is S prime. P power gamma plus 1 for some S belonging to N, S prime. Such a formula I get. Because the remaining guys are just cardinality argument. Now the left side is equal. So right sides are equal. And this is 1. So this is 1 because the group is cyclic. So this is 1, this is equal to this. Therefore, what do I get? I get. So collect. I am interested in this. So in this, I am going to cancel P power gamma. I am going to cancel P power gamma. See here. So, and I will keep this one side. So what do I get? I will write here. D, we are interested in D beta. D beta G. I have cancelled P power gamma. So this is only purely number. So you can do any calculation. So Q, that is this Q, plus S times. So the P terms, after cancelling the gamma, there is one P definitely left. So that I am going to shift it to the other side. So this I am going to shift it to this side. So this is congruent to, and I'm going to divide by P, both the sides. So this is congruent to, this is 1, I have cancelled P gamma, this is Q, and this will vanish because I have read mod Q, so mod P. Is that mistake? Did I do any mistake? No. Agreed? Sonakshi, do you agree?
Sir, can you explain this again?
Okay, so Sonakshi, we have these left sides are equal.
Yes, sir.
I have this side equal to this side.
Yes, sir.
In this side, I have P gamma, P gamma, P gamma plus 1, P gamma plus 1. So first
Yes,
of
sir.
all, what I am going to do is, when you write this equal to this, I am going to cancel P gamma on both sides.
Okay.
So I have cancelled this P gamma. So let me cancel it here. This is gone. This is gone. This is gone, but the one P is left.
Yes, sir.
This is gone and one P is left. One P is left here. So P is
Yes,
left here, P is left here. Now I am going to keep this term on one side and this P I am going to read mod P. So when I
Okay.
read mod P, this will disappear altogether.
Yes, sir.
And this will be left only d beta g.
Yes, sir.
So that's what I have written. D beta g q is left here.
Okay.
And here this P gamma is gone. So this I am shifting into the other side. See, this is the other side, no? This equal to this side. So this d beta g q mod p, this is gone. So the other side left is d beta zn, which is 1 I know, and this q is left, and this is also multiple of p. So this is also gone. So isn't these two are congruent?
Okay. Okay. You
Correct?
use this bracketed formula in that.
Sorry.
So you also use this bracketed formula for d beta g zn equals to
Of
1.
course, of course, of
Yeah.
course.
Okay. Okay.
So I got this. Now from here I want to conclude. I can cancel this q. Why? Because q is co-prime to p. So we'll get d beta g is congruent to 1 mod. Since p doesn't divide q. P doesn't divide q means q is a non-derivative either mod p. Z mod p is a field and q is a non-zero element there. So I can cancel. So I proved one. I proved the first theorem. I proved the first theorem. Where are the first theorem? Here. The number of subgroups of order p power beta is d beta is congruent to 1 mod p. All right. Anybody still have difficulty? I am willing to answer. So this finish proof of 1. This proves first Sylow theorem. More than that actually. It proved not only first Sylow theorem, but it also proved the similar thing for any subgroup of any divisor p power beta, not only the highest power, but even smaller powers. Agreed? Sonakshi.
Yes, sir.
All right. Now let us head on to proof 2. Anybody has a difficulty, please? Roshini.
It's clear, sir.
Huh?
It's clear, sir.
Clear. Rahul.
Yes, sir, it is clear.
Don't hesitate to ask question. Nothing will happen.
No, sir, it is clear.
All right. So the other people, anybody has difficulty? This is very, very important theorem. And this proof you will not find in the books. I will tell you what Einstein do. This proof is little different from Einstein. Einstein look at this number, this binomial, and expand by binomial theorem. And then claim that all the coefficients are divisible by p. And then does similar calculation. But I'm not using that. In fact, that is a corollary now. All right. So in between, I will mention that in the due course of this proof of 1, we have proved this corollary that I will state. So corollary What we proved, this is completely combinatorial corollary. What did we prove? P is the prime number, P prime. Q is a natural number, non-zero, P doesn't divide Q. And alpha or beta gamma are two natural numbers. Then we have proved if I take this binomial coefficient P beta plus gamma, Q, choose P beta, this is congruent to P power gamma, Q mod P power gamma plus 1. This is what we have proved. I didn't cancel that and read mod P power gamma plus 1. Here I didn't cancel and I read mod this. And then this is obvious. So that's a corollary. All right, anyway, we have proved one, and now let us prove second. Second will not take so long time. I'll finish it in 5 minutes. And third will also be similar. All right, so second, what do you want to prove? We have given the GCD of P and Q is 1. P is the prime number and its co-prime to Q, therefore GCD is 1. All right, so now what is you want to prove? What do you want to prove? Let me see. You want to prove that if H and H is a subgroup of order P power alpha and H prime, this is prime here, H prime is of P power beta, then you can find one G so that this H prime is contained in the conjugate of H. And in particular part will directly follow. If both are of P power alpha, then this has to be equality, and that means any two Sylow subgroups are conjugates. This is what we want to prove. So start with two subgroups H and H prime. And cardinality of H is P power alpha. And cardinality of H prime is P power beta. And alpha is bigger equal to beta. That is given. And what are you looking for? Write down there. Looking for an element G in G with H prime is containing G, H, G inverse. This is what we are looking for. So you want to get hold of G. How can you get hold of G? It's like this. So consider we have given H. So consider the G space G by H. By left translation. I said D. So by left translation. And we know this is homogeneous. This has only one orbit. This action is transitive. That we have studied. And I'm going to restrict this operation of G on this. So restrict this operation. This operation to the subgroup H prime. In other words, I'm considering the H prime action by left translation on this G by H. Now I don't know whether it is transitive. So remember, this operation is H prime cross G mod H, G by H to G by H. And what is the operation map? Any H prime times any coset, that is going to H prime GH. That is the operation explicitly. And I want to use the class equation. So my set is X by H, G by H. So the cardinality of G by H, that I know what is this. This is precisely Q. Because cardinality of H is P power alpha. Because of this. So this is the cardinality is Q on this side. And this is cardinality equal to the fixed points of the H prime action on G by H plus cardinalities of the orbits which has more than one element. So cardinality, so this is sum of the cardinalities of the orbits, H orbits, I should say H prime orbits, orbits under H prime. And that cardinality I know, that is the index of the stabilizer. So that is H prime times the stabilizer of these orbits. So that is, what do I denote? Stabilizer, let me just write. Or let me write GH and suffix some orbit. So orbit. But anyway, it is indexed in H prime. And H prime is a P group. Order of H prime is P power beta. So it's a P group. And so these indices, they are more than one because cardinalities are more, or orbits are bigger than one. So therefore they are all divisible by P. So all these guys are divisible by P. P divides all of them. All these guys. And when I read this equation mod P, what will happen? What will happen? I want to read mod P. So Q is congruent to the number of fixed points. So this also should be number of fixed points and this will disappear, mod P. And this Q is not zero. This Q is not zero mod P. This is not zero mod P. So therefore this cannot be zero mod P. So that means number of fixed points of this H prime space is non-zero. That means there is one fixed point. This is mod P. So that means this fixed point cannot be empty. That means what? There is a left coset. So that means there exists a left coset GH in G by H such that what? Which is invariant under all elements of this H prime, such that H prime times GH equal to GH for all H prime in H prime. So that means H prime. So I want to keep H prime on this side and remaining the other side. What do I do? So you first multiply by G inverse H prime GH equal to H for all H prime in H prime. So that means H prime belongs to G, H, G inverse for all H prime in H prime. And that means H prime is contained in G, H, G inverse. Finished. Done? Any question? Sonakshi, is it okay?
Yes, sir.
All right. Now let me finish off 3. It will take 1 minute. So proof of 3. So what do you want? 3? 3 is what? 3. The number of Sylow subgroups divide Q. That is 3. This. All right. So take 2 Sylow subgroups. Take H and H prime, 2 P Sylow subgroups. Not only, take only one. I want to count the number of Sylow subgroups. So start with the Sylow subgroup H. And now you take any other subgroup, any other subgroup of order P power alpha. That means any other Sylow subgroup. I know by 2 they are conjugates. So if you call it H, H prime, then H prime is the conjugate of H, G in G. We have proved in 2 it is contained in, H prime is contained in the conjugate, but now H prime also has the same cardinality, so equality here. So this is by 2. But now I need some statement which already we have proved it. So how many conjugates are there? So okay, think about this now. I will complete this next time. I will have to recall something which we have proved earlier. All right. All right. So I will stop here. Sorry if I exceeded the time, but I wanted to finish. But still, I have to recall something here, which will take maybe 5 minutes, not more. But this proof is very, very clean. And then the next time I will give 2 more proofs. And as you see in the literature, there are many number of proofs. But my personal choice is this proof. All right, so I will stop here. If anybody has a question, please still raise it. I will make a PDF file of this and immediately send to Makaran.